So here we go, part two, convergence. Now, um, hopefully we'll get through all the convergence and do the transform and the other. But if we don't, we don't. So we're just going to take our time as we walk through this. So where we left off, we had made plates at divergent margins. That's where we make ocean type crust. And this is probably the original crust of the Earth would have been mafic ocean type crust. So the Earth is not expanding, at least not as far as we can tell. And so if we're making crust somewhere, then it must be going away somewhere else. And what we find happens is that oceanic crust, as it cools and gets older and collects sediment on top, it gets more dense, and it actually ends up returning back to the mantle. And that's what gives us what we call a subduction zone, which happens at convergent margins. So here we have two pictures of ocean type plate, and I keep saying crust, but we got to remember that there's lithosphere here, so it's crust plus the solid rigid mantle material attached underneath. And the reason I keep emphasizing that is because if you just looked at the crust that's on top, the density is only in the neighborhood of 2.8 to 3 grams per cubic centimeter, which would not allow it to sink back into the mantle. The mantle's average density is around 5 to 5.5 grams per cubic centimeter. But if you look at this picture, you'll notice that most of that plate is mantle material. And when it's cold, it gets more dense, and that's what allows it to sink back down and take that thin layer of ocean type crust that's on top with it. So let's talk about what happens at this type of boundary. We can again do a thought experiment like we did when plates pull apart. What would happen when these two things run into each other? And the first thing we see, the first thing on our list here is subduction. And subduction simply means one plate is going underneath the other. So you can see they have one of those labeled as subducting lithosphere, and it moves toward and then underneath the other plate. Now, this results in several things happening. They're all going on at the same time. But number one, when one plate goes under the other, there's going to be a low spot in the ocean, and that is the trench. So the trench marks the location of where the subducting lithosphere is going back down and going underneath whichever piece of lithosphere ends up on top. And the piece that ends up on top is typically, we find, the younger piece that is warmer and less dense. Now you'll notice that right next to the trench, they have a wedge of material there, and we call that an accretionary wedge. So as you might expect, if one plate, and this is rigid material, is being pushed under the other, things that are on top of that plate, sediment, maybe a little island that's sticking up, that material will not go back down with the subducting lithosphere, and instead it gets scraped off. A fun activity that you can do at home to see how this works is take your two hands. On one hand, put frosting, and then push that hand underneath the other. And as you do, the hand on top will scrape off the frosting, and that is your accretionary wedge, which you can then eat. So what else happens? Well, the next bullet you'll see here is it says partial melting of mantle. What's going on with that? Well, this gets a little more complicated, but that subducting lithosphere is wet. It's wet with water from the ocean. It was ocean type crust on top there. And so some of that seawater sinks in and soaks in and becomes part of the lithosphere. When it gets into the upper mantle right in here, it triggers a chemical response. And what happens is some of the minerals in the overriding plate with the addition of water, reach their melting point. And there's some graphs and things to kind of show how this works in the book. But the way we simplify this is we just say it melts because we've added water. Now, one of the key things to understand about this is not all of the minerals present reach their melting point. And so the resulting molten rock, instead of being mafic, is intermediate to felsic. The minerals that melt are the felsic to intermediate minerals, or at least those are the ones that dominate. And so that's what makes up our molten rock. So we start with mafic material, but we only melt some of the minerals, and those are the ones that form the molten rock, which then rises to the surface. So we get intrusive igneous rock, which is going to be granite and diorite, pink and gray rocks. And then when they come out on the surface, we get volcanoes. And if you remember back to our discussion of volcanoes, this is the type of rock that will give you stratovolcanoes, which tend to be very tall and pointy and also tend to be explosive. Now, because the surface of the Earth is curved, the subduction zone tends to be curved as well. And so we refer to this row of volcanoes as a volcanic arc instead of a volcanic line, because when we look at it on a map, it is typically curved. The other thing that happens that is not really depicted on this drawing is that we get the results that you would expect with high pressure convergence, which is folding of the rocks, reverse faulting and associated earthquakes, and also this whole region is going to be a focus of metamorphic activity. So if I draw this on the board in the classroom, this drawing quickly gets very, very busy. I have to use every color of marker I own in order to depict all the different things that are happening. And this is a very, very complicated margin, geologically speaking. You might imagine the material accreting here is mostly sediment. It then gets folded and faulted and metamorphosed as it gets pushed into this volcanic arc, and at the same time there are igneous intrusions coming in as well. So this is a very, very busy, active place, geologically speaking. So this slide is just a close-up summary view of what was on the previous slide. It shows us the volcanic arc, the water triggering the partial melting when the subducting slab releases it. We've got our accretionary prism or accretionary wedge. We've got our trench. The only thing they don't highlight on here is the folding and the reverse faulting and the metamorphic activity. So where can we find one of these convergent boundaries? We're actually going to take a look at a couple. This is a relatively new one. We know it's relatively new because the volcanic arc, the volcanoes are fairly small. So they're just starting to pop up out of the ocean. You'll notice that the crust thickens here. And this is, I should mention, this is where we make continental type crust. So as this molten rock rises up and cools and solidifies, and as this sediment is scraped off, together they make our continental type crust. You'll notice this feature is fairly stable. So the longer this subduction zone exists, the more material we're going to add here, and we're going to get thick crust, which is one of the markers of continental crust. And we're going to make it with a lot of felsic to intermediate rocks, which is the composition type for continental type crust. So this is a place where we see this kind of in the early stage. You can see this is the Aleutian Islands. So this is Alaska, the Bering Strait, and this is Siberia. So we have this, you can see why they call it an arc. It's got a nice curved shape, and it goes into another one. This is the Kamchatka Peninsula, which is also a subduction zone and has a lot of active volcanoes as well. The next map we look at is Indonesia. This is our trench right here. This particular trench, when it popped a few years ago, created a very large tsunami that devastated an area around the Indian Ocean. This is India and Sri Lanka over here. And it's these subduction zones that generate some of our biggest tsunamis. Now you'll notice here we have some extra islands popping up. Now the volcanic arc is located on these islands here in Indonesia. There was a pretty famous explosion here in the 1800s. The island called Krakatoa is right there in the middle, but that's part of the volcanic arc. This is accreted material that's building up to the point where it's being pushed up and becomes land and some extra islands there. So this is what our kind of a mature subduction zone looks like. Now, you might say, what happens if the crust involved is continental on both sides? And we will get to that in a moment. I want to talk about this first, ocean-continent convergent. So we talked about ocean-ocean, and here was our original slide. And what you'll notice that the ocean-continent convergence is basically the same thing you have with the ocean-ocean convergence. We still have our subduction, we still have our trench. We have high pressure convergence. In this case, it's built to the point where it gives us a large mountain range. We get folding and regional metamorphism depicted here in purple. We get reverse and what they call thrust faulting, which is just a special type of reverse fault that has a very low angle where one side thrusts up and over the other. We still have our accretionary wedge right here that's got material scraped off the subducting plate. We still have our partial melting of the mantle, which means that in the middle of our mountain range here, we're going to have some volcanoes. So in this case, our volcanic arc, instead of being islands, is going to be located in the middle of the mountain range. So where can we find something like this? Well, the classic example is the west coast or the west side of South America. There is actually a volcanic arc and a trench in the Pacific Northwest. So if you think of Mount Rainier and Mount St. Helens, they're part of a volcanic arc. And there's a trench right off the coast there. That trench is not as prominent a feature on the ocean floor, so this one is a little bit prettier in the picture, and so that's why I picked it. These are the Andes Mountains here, and mixed in with that mountain range are a series of volcanoes. And I think what I'll do is we'll have one more short presentation to show you what happens when a continent comes in from the other side, closes up the ocean basin, and slams into that subduction zone. And what you'll notice on this diagram is that subduction is not going to happen. It's not going to continue. But we'll leave that for the next set of slides.